So what we've done up to here is really all of the physics. And I need to correct one thing. I don't want to confuse people here. I really should have called this F sub n. So this is all of the physics, right, to get to really this point. From here on out, we're really just looking at algebra. And it's kind of a messy algebra problem, but it is worth doing so you can see how to deal with this. So we want to remind ourselves what we're looking for. And so I've got two equations and I've got this mu, which I'm looking for. But I also have some unknowns of masses and normal forces. I know theta, and I can get at the acceleration because the acceleration is v squared over r. So the acceleration is actually 70 meters per second squared over 305 meters, which I calculate to be about 13.9 meters per second squared. So I know this number, and I know g, and of course I know theta, cosine and sine of theta. So what I'm going to do is show you how we get at the different pieces of this. So I'm going to take my two equations, this equation number 1 and this equation number 2, one for x and one for y, and start solving one for the other in terms of some unknowns. And probably the easiest way to work this is to, because every term, I've got an m and something on one side and then force normal everywhere else, is to actually just solve problem 1 for m and say m is equal to force normal sine theta plus mu force normal cosine theta over the acceleration. And then, so that's from 1. And then from 2, I've got something similar, which is m, if I just bring this mg over to this side, mg equals force normal cosine theta minus mu force normal sine of theta. And then I divide both sides by g. Okay. And then I have two equations for m. M is unknown, but I can equate these. So I'm going to say this is equal to this expression. And notice what happens. My force normal, every term has a force normal. So I have force normal sine of theta plus mu force normal cosine theta over a is equal to force normal cosine theta minus mu force normal sine of theta over g. I divide by force normal, and so I divide this side by force normal and this side by force normal, and because it's in the denominator in both places, I can go term by term, or I can factor out a force normal, however you want to think about it. And I'm going to cross multiply these a's and g's through just so I don't have any fractions. And so I'll multiply this side with an a, which will multiply this side by an a. And then I'll multiply this side by a g to cancel that there, which means I need to multiply this side by a g. This a cancels. And I'm finally left with g sine theta plus mu g cosine theta is equal to g cosine theta minus mu g sine theta. And then I'm really solving for mu, which I could have done to start with, but I thought it was a little clearer to do it this way, as I need to get all my mu's on one side and my other terms on the other. So I'm going to add mu g sine of theta to this side, so I'm going to add it over here, plus mu g sine theta, and then I'm going to subtract g sine theta from this side, which means subtract g sine theta over here. Okay, so finally I have mu g, oh, I should have canceled out all the g's. Sorry, we had g's. No, we don't have a g on this side. My bad. We have an a. I need to fix my expressions here. Let's see. So I have an a, this a, sorry, a. So I need an a instead of this. Gotta catch your errors. And this one is still a G. Okay, sorry. So we've got a mu A sine theta plus mu G cosine theta is equal to, then I think I got this, A cosine theta minus G sine theta. That looks okay to me. And so finally my mu factored out of this term, so I can factor it out of both terms there, is equal to A cosine theta minus G sine theta all over A sine theta plus G cosine theta. Okay, sticking some numbers in is what we have left to do, and I have that cosine of 31 degrees is 0.86, sine of 31 degrees is 0.52. Our acceleration we found to be 13.9 meters per second squared, and G of course is 9.8 meters per second squared. And when we put all of those in, I get mu is equal to, I get 11.9 minus 5.1 meters per second squared on the top, all over 7.2 plus 8.4, again meters per second squared. Those cancel as they should for unitless things, and I get a coefficient of friction of about 0.44. So if we look in the book at our table of car tire or rubber on cement, on dry cement, that mu is equal to 1. So we're in good shape. If we're on wet cement, when it's wet, if it's a rainy day, then we're looking at a mu of 0.5 to 0.7. So then we're getting closer to the danger zone here of where we might slip off the track. But you can see, I mean, yes, it's a lot of algebra, but the basic idea is the same as what we've done before. It's just starting with a force diagram that looks like this, and then unpacking what it means depending on what information we need to find. We've got to be careful about our trig, and then we continue to divide things by components, right? So components, components, components. And we need to pay attention to which components, how we set up our axis so we get an acceleration of 0 in one of the directions. That just makes things easier. And then we move along and just do our algebra as we need to, and hopefully we don't make mistakes.